Welcome to week 10 of Classical Mechanics 2. I'm Sabata Matsumoto. This week we'll be discussing both the calculus of rotations and the angular momentum tensor. Last week we showed that in bodies that are both rotating and translating, the angular momentum can be decomposed into two components. An orbital component, which is the same as the angular momentum of a point object with the same mass as our rigid body, translating past our origin. And a spin component, where the body itself rotates about its center of mass at some rate, omega prime. In the case we discussed last week, it was assumed that the rotation was about the center of mass. However, that needn't be the case. It turns out that motion, where the rotations aren't passing through the center of mass, can be treated in the same way, thanks to Chasles' theorem, which states that the instantaneous motion of any rigid body can be written as the translational motion of a point P with some velocity v, and the rotation about some axis passing through the point P, although this axis may change over time. I'm not going to prove this for you since it's a lot of algebra and none of it's really insightful. What about the coordinate systems themselves? We'll soon find out that having a coordinate system that's stuck to the rotating body makes calculations much easier. It will be helpful if we know how rotating coordinate systems behave. If our coordinate system is rotating at angular velocity omega, then a point that is a distance r away from the origin is traveling at velocity v, where v is equal to omega cross r in the lab frame. Similarly, in coordinate systems that rotate at a constant rate, time derivatives behave in the same way. For some value u, the time rate of change of u in this rotating coordinate system is merely omega cross u. We can extend this idea to multiple coordinate systems spinning together. Let's start with coordinate system S1. Coordinate system S1 is spinning around coordinate system S2 at rate omega 1, 2. Coordinate system 2 is rotating about coordinate system 3 at rate omega 2, 3. This implies that coordinate system 1 is rotating about coordinate system 3 at the combined rate omega 1, 3 is equal to omega 1, 2 plus omega 2, 3. Imagine now we have a point P in the lab frame. It's traveling at velocities Vp is equal to omega 1, 2 cross P in coordinate system S1. It's traveling at Vp is equal to omega 2, 3 cross P in coordinate system 2. And in coordinate system 3, it's traveling at Vp is equal to omega 1, 2 plus omega 2, 3 cross P. An example of this is this rotating sphere. It's rotating at angular speed omega 3 about a stick that initially points in the z direction. You grab the stick and rotate it in the y direction at angular speed omega 2. Right after this kick, what is the angular velocity in the lab frame? The new angular speed is omega 3, 2, which is equal to omega 3 plus omega 2. This implies that instantaneously, there's no motion along the line of points parallel to omega 3, 2, along this direction, which is anchored at the origin. As the motion continues, the vector omega 3 will change directions. While the new rotation will still be omega 3, 2 is equal to omega 3 plus omega 2, there won't be a single fixed line of points throughout the whole motion. This is an example of why coordinate systems that are fixed to the objects might be more convenient. We know that omega 3 is always going to be rotating about the direction that this stick is pointing in, while omega 2 is some direction orthogonal to that. Now that we understand how rotating coordinate systems behave, in the next video, we'll look at the moment of inertia tensor, and we'll see why we need all of this algebra for future calculations. See you next time. Similarly, in we can extend this idea to coordinate systems plus omega 23. Let's try that again. Similarly, in coordinate systems, the new angular speed is omega 23,